Okay, so 8-1 is referred to as a single population mean using the normal distribution. What we're going to do here is we're going to conduct a process. It's called they're called confidence intervals. We're trying to find and locate what a confidence interval is. And through the entire chapter, basically what we do is say, okay, how do I find the confidence interval when I don't know the population mean, but I know the standard deviation? Okay? Or maybe what do I do if I know the population mean, but I don't know the standard deviation? Or so they start giving me certain criteria out of the statistics that we either know or we don't know. And based on what we do know and what we don't know, it kind of leads us down a certain pathway to find what we call a confidence interval. Okay, this is probably 8-1. Like most sections, the first kind of section is the easiest to kind of work with. But in all actuality, the things that we go through here in a little bit, it's going to be rare that exists kind of in real life. Okay, but it gets the ball rolling. It gets us to understand the concept, and then in 8-2 and 8-3, we'll see things that are really more real-world applicable for us. Okay, but kind of getting the understanding of what's going on here. This scenario says suppose you want to find the mean average of a particular car, its price in your area. Okay, so maybe you've budgeted and maybe I have $400 budgeted a month for a car, and I really like this car. Can I swing that? What's the average cost before I even go like car lot to car lot or whatever, and actually look at cars? Okay, so I just want to find out what model is going to work for me, okay, in my budget. So you do a little bit of research. You get online. You go drive by car lots, and you start recording prices. Okay. And maybe you get 10, 15 prices, and you average those. Okay, so let's say we take these 10, 15 car prices, and we average them. And let's say we get the average to be, let's see here. So it's a sample, so let's just call it X bar. And let's say we get that to be $25,000. Okay, and let's say our N, like I said, was 15. Let's say 15 cars, 15 prices. Okay. What that is saying is there are cars that are above $25,000 in my 15 size sample, and there are cars that are below the $25,000 range in that 15. Does that make sense? There could be cars in there that are exactly $25,000. But what we'll find out eventually is that that's kind of unlikely. Okay, we've talked in the past that our statistic or our parameter, like a mean, okay, X bar or mu, doesn't necessarily and usually isn't one of the specific values that are in your population or your sample. Okay, but this is an estimate of the middle. Okay, of the mean. Okay, so there's values above it and there's values below it. Because it's a singular value, we call that a point estimate. Okay, and it's, if you think about it, if somebody asks me, well, you're going to go buy this new car. You've done this research, you're going to buy this new car. What's the probability that's going to cost you $25,000? It's probably a very, very low probability. Because it's probably going to cost you a little bit less than $25,000 or a little bit more. Does that make sense? But on the dot, $25,000, it's very, very unlikely for that to happen. Okay, because it's a point estimate. So it's the idea if I'm trying to, if I'm playing darts or something and I want to find the probability of hitting that little dot right there in the middle, that's a low probability, right? But if I open my target up and say, now hit that shaded region, greater probability, correct? So what's the probability of hitting exactly that value when I go to the car lot and buy the car? Very low. That's going to be a very low probability. It's going to be $25,000. But if I open my range up a little bit and say, okay, well, what's the probability that you pay your car to be between 23.5 and 26.5. Now, there's a greater probability that your car that you paid for is in that interval. Does that make sense? Okay. So that's the idea. This is referred to as a point estimate. This is referred to as a confidence interval. Okay. It says we use sample data to make generalizations about an unknown population. We know nothing about all of these cars. Okay, maybe I pick out one make and model of a car. We don't know the entire population. Every car that's made, maybe from that manufacturer. Okay, but we can take samples. Okay, so it says here we take the sample data to make generalizations about the population that we have no knowledge about. It says this part of statistics is called inferential statistics, making inferences. Okay, inferences are like making guesses. Does that make sense? But they're educated guesses. Okay, they're guesses based off of data and known information. Says the sample data help us to make an estimate of a population parameter. So you know nothing about the population parameter mu. But we're going to take these samples and we're going to work with these sample sizes and these means of these samples and make, based on those samples and the means of those samples, we can make an inference, a guess, but an educated guess, about the population parameter that was not known. Okay? It says the point estimate is most likely not the exact value of the population parameter. So that $25,000 is most likely not the mean of the population. Okay? But it should be close to it. Okay? It shouldn't be real far off. Okay? So it should be in the ballpark. It says after calculating the point estimates, we construct interval estimates. And these are called confidence intervals. And these things are what we're going to spend a bulk of the rest of the year working with. Okay, there will be components to a lot of the things that we do in the next couple chapters. So a confidence interval is another type of estimate, but instead of being just one number, it's an interval of numbers. Okay, it's a series of numbers. So the interval of numbers is a range of values calculated from a given set of sample data. The confidence interval is likely, keyword here, likely, to include an unknown population parameter. So if I say that my confidence interval is $23,500 to $26,500, it is likely, from the research we've done and the samples we've looked at, it is likely that the population mean, even though I don't know what the population is, and I don't know what the mean is, it's likely that that population mean is between those two numbers. Does that make sense? Okay. So the confidence interval for a population mean with a known standard deviation is based on the fact that the sample means follow an approximately normal distribution. So we're going to use the normal curve here. And in order to use the normal curve, we need a normal distribution. That paragraph right there, I guess sentence, allows basically us to realize that the central limit theorem is going to be used here, okay, so that we can realize a normal distribution. Okay, and basically all we have to do is make sure that we understand when we're taking these sample means is that we use a sample that is 30 or bigger, and that will then allow the normal distribution to be there. Okay. It says in an interval estimate, the parameter is specified as being between two values. Remember, parameter is a numerical characteristic for a population, okay? And we're talking about means here, so in our case, it's going to be mu. It says, for example, an interval estimate of the average age of all students might be 26.9 years to 27.7 years, okay? So that is a range or an interval of values, correct? Okay, so we might have a particular confidence interval, confidence level, that we're in. Maybe we could say we are 90% confident that the average age of students falls between those two numbers. Does that make sense? Okay. Now, let's think about this. If I am, right, I know not everybody is a sports fan, but just kind of draw. You guys all know what I mean by field goal, right? When I say field goal for football. Okay, so you got these goal posts, and we're going to kick a ball through them, right? We good with that idea? Okay, all right. So let's say, so this is the high school field goal post. Those are college. And these are pro. Okay, yes. So, if I'm a pro, okay, how can I phrase this the best way? If I'm going to kick a ball through here, well, let's say that, let's not say I'm a pro or whatever. Let's just say that we're a random person kicking a ball through here. Which one of these would you be more confident in making a field goal with? Top one, middle one, or bottom one? You'd be more confident up here, right? Okay, because the goalposts are further apart, right? You have more wiggle room for error, correct? Does that make sense? Okay, so what we would say, what happens here is if I want to be, in statistics, if I want to be 99% confident in my interval containing my mean, then my goalposts are going to be very narrow. Okay? If I want to be, actually, let me phrase that. If I want to be 99% confident that I'm going to make a field goal, then my goalposts actually need to be wider. Okay? The less confident you are, so let's say this is 95% confident. Okay? Now, I can bring my window down. Okay? Because now I'm not as confident of making it as I was up here. Does that make sense? And then down here would be like 90% confident. Okay? The narrower the window that you have to kick the ball through, the less confident you are in making it. Does that make sense? Is that okay with everybody? I don't know if that's the greatest analogy, but with confidence intervals, okay, usually we want our confidence to be in the 90s, 90 to 95 to 99. Those are usually the three main confidence levels that we use. When the confidence level increases, the interval needs to increase as well. Okay, so the more confident I am in something, the wider this interval becomes. And it's just like this idea here. I'm more confident making this kick here. I'm more 99% more confident to kick and make it here than I am down here because this window is larger. Does that make sense? So I'm just trying to give you an example or an idea of what should happen as we change our confidence interval. We'll see some examples of this, practice examples of real numbers, and see how that window changes based on our choice of confidence. Okay. Now, this choice of confidence is usually something that the designer of the study is going to choose. Okay. And most of the time you see 95 and 99. Okay. Occasionally see 90. But if I want to be like 50% confident, we can do the work. Okay. But I don't know that you would ever want to publish something that says I'm 50% confident in my work. Okay. Or 30% confident. The higher the confidence, the more kind of validated your work is. Does that make sense? Okay. So it's either the interval contains the parameter or it does not. Okay. Because we can't be 100% certain. Okay. There is never 100% certainty. Okay. So your interval might not have the parameter in it, but a degree of confidence will allow us to make the argument that we're getting close, or we have a very, very, very good idea that it should be in there. Okay. Like I said, you'll get to choose, or the problem will tell you, hey, this researcher wanted a 95% confident level, or a 90%, or a 99, or whatever. Okay, so that'll be either something we get to choose, or they tell us. A lot of problems you'll see, they'll ask you, figure out this problem with a 90% confidence level, now figure it out with a 95, and now figure it out with a 99, and then compare your intervals, okay? You'll see that widening or narrowing of the interval as these change. Is that all right with everybody? Okay. Another way of thinking about this is if we were to take, so let's say that we want to be 95% confident, okay? What that really means is if I were to take, let's say this is the interval for 95%, the argument then is that if we were to take samples over and over and over and over and over and over again, 95% of those samples will have a mean that is between those two numbers. Does that make sense? There'll be 5% of those samples will have maybe a mean that's like 26.2. Might be a mean that's like 28.1. But 95% of them will be in between those two. Does that kind of make sense? Okay. So those are two ways that we can think about what a confidence interval is doing for us. Calculating the confidence interval. Okay. I don't really care for the way that OpenStax, our textbook, uses some notation. And you'll see this from stat book to stat book. I've taught out of 3 or 4 different stat books in the past, and just holistically over all textbooks. It doesn't seem like there's really a uniform notation for a lot of things, okay? I don't like this where they say EBM here, okay, but I'll explain that to you in a moment. But I'm going to try to show you multiple notations for some of this stuff. It says to construct a confidence interval for a single unknown population mean where the population standard deviation is known. This scenario is rare, okay? Think about this. How do I find the standard deviation? Isn't the standard deviation found by taking the square root of the sum of x minus mu divided by n? Isn't that how we find standard deviation?
You're asking the wrong girl.
That's mu, right? Mu is the population mean. Correct? So what they're telling me here is that you know the standard deviation. You know what this thing here is going to yield, but you don't know the component here that helps you generate that value. Does that kind of make sense? You see how this would maybe kind of be rare? Okay. So that's where maybe this type of situation, 8.1, gets the ball rolling with what we do. But might not be something that we really realize or is extremely applicable for us in the future. What we'll probably have more knowledge about in the future is not this standard deviation, but we'll have knowledge of the standard deviation of the sample means, okay? And that's where 8.2 and 8.3 will take us, okay? But again, understanding the kind of the foundation using this first, okay? When we do this, so if I want to try to find an interval for a single unknown population mean mu, where the population standard deviation is known, we need x bar, okay? So we need a sample mean, okay? And that's the point estimate of the unknown population mean. And once we have x bar, we're going to then find this thing called EBM, okay, which I don't like it because EBM is what we refer to as our margin of error, okay? And basically what our margin of error is, if you go back up to this confidence interval right here, I wrote it 2 different ways. I wrote it that way, but if I find the center of those 2 values in my interval, the center is 27.3, okay? And to go from 27.3 to that number, I add 0.4. To go from 27.3 to that number, I subtract 0.4. 0.4 is referred to as our margin of error, okay? It's essentially the freedom that is provided for that point estimate so that my parameter, maybe we're 90, 95, 99% confident that my parameter falls in between those two values, okay? So 27.3 in this situation would actually be my point estimate, okay? So it's called margin of error. They call it in our textbook EBM, okay? EB standing for error bound, okay? And you're gonna have an upper bound and a lower bound. So I believe, and I could be wrong, but I think EBM stands for error bound measurement, okay? I'm gonna use the words margin of error, okay? But you might see Math Excel throw in EBM every once in a while, so just be cautious of that. But basically the way we find a confidence interval is we take our point estimate and we subtract our margin of error, and we take our point estimate and we add our margin of error, and that gives us the lower bound and the upper bound for our interval, okay? It's really not a hard task. What's difficult, or will be more difficult, is actually there's a formula for finding margin of error, okay? So we'll have to get into how we do that. Or how to find that 0.4 in that specific situation. And that will change, okay? Like I said, that 0.4, my mouse stopped working. Well, part of it stopped working. There we go. This 0.4, as my level of confidence either increases or decreases, this 0.4 might grow or it might shrink. That make sense? Okay. Confidence level is abbreviated capital CL. Okay. It says the confidence level is often considered the probability that the calculated confidence interval estimate will contain the true population parameter. So the likelihood that the parameter is inside this interval. Okay. Or you could think about it as if we were going to do this, take this sample infinite amount of times, or over and over and over again. It's the percent of times that the population parameter will exist inside that interval. Okay, so that was the idea. If we take 15 cars up here, take samples of 15 cars over and over and over and over again, maybe there's maybe 95% of those, if we have 95% confidence level, 95% of those samples that we took over and over and over again will fall between those two numbers. Okay. Again, when we see more specific scenarios tomorrow and the next day with kind of context with, like I said, specific situations, those arguments and concepts will be easier to talk about. Questions on this so far? We're good? There is another probability. This is the last thing. It's not on that paper, so you might want to add this. There's another probability we call alpha. Okay, and essentially we talked about this back in the chapter 2 and 3. And we're talking about complements, right? 90% chance it's going to rain, then it's a 10% chance that it's not going to rain, right? Well, if I have a confidence level of 90%, that there is a 90% chance that my population parameter falls between these two values, then there's a 10% chance that that doesn't happen, okay? That 10% chance, the complement idea essentially, is what we're calling alpha here, okay? So alpha is related to the confidence interval, okay? It's the probability that the interval does not contain the unknown population parameter. And mathematically speaking, alpha plus your confidence level should equal 1. And that work right there tells you alpha is equal to 1 minus confidence level. And that was the definition of complements when we talked about probability. Kind of the last thing, kind of give you an idea of where we're going to go tomorrow. What's going to happen? So we're going to make the assumption, because we're going to take samples that are big enough, that our sample means are going to be normally distributed. Okay? And we will not know our population parameter. Okay, we will not know the mean. However, what we will do is we'll say we want to be 90% confident, 90%, 95%, 99% confident that our population parameter mean, mu here, will fall between two values. So maybe if we go back up to, what was that number, 26.9 and 27.7, we will say 90% confidence that our mu is between those two numbers. Does that make sense to everybody? Okay. That means our mean might not be between those two numbers. Our mean could be out here. And if that's 90%, okay, and everything is symmetric here, right? Okay, so if that's 90% centered on the mean, does it make sense that that is 5% and that that is 5%? Is that okay with everybody? Okay, so this area here that is red, we would call alpha over 2. Because it's everything that is red would be alpha. Okay, just one, we call these tails. This would be the left tail. This would be the right tail. But the way that we set these up, these confidence intervals, is that they should be symmetric about the mean. So if I want 90% confidence, maybe I go between 26.9 and 27.7. Okay. Now if I want this to go up, if I want that to be maybe 95% confident, if I want to be 95% confident, that means that these boundaries, they need to be moved over. They need to be widened. So now I make a bigger interval, essentially make my goalpost bigger now, right? Does that make sense? And now I can have a greater confidence. Well, if I have a greater confidence now, and this is now 95%, now my tails would both be 2.5 and 2.5. Does that make sense? Okay, so that's kind of where we'll go tomorrow, and talk about how do we find that EBM or that margin of error so we can actually construct our confidence interval. Okay, what's going to happen with confidence intervals is, have you guys ever heard of the terminology of hypothesis testing? Ever heard that before? Like a null hypothesis, you ever heard that phrase, that word? Okay, so we're going to get into being able to either accept or reject null hypotheses in the future to make sure, like maybe doing research on like a medical drug, we can make, we might have a hypothesis that there is a benefit of this drug. And the statistics will then tell us, yes, there was a benefit, or no, there was not. In order to do that, we need to first have confidence intervals established. Okay? And if we don't have those, then our hypothesis testing is moot. Okay? No homework tonight. Tomorrow, hopefully, Schoology will let me get some things posted on it. If not, I'll print off what I've got for you, and we can go along that route. All right? No homework.